Okay, let's have a class, and we will talk is an important topic today called the lipids oxidation. So that is a key of the for the chemistry section. So lipids oxidation. First of all, we will briefly review what we talked already. Where will happen a lipids oxidation if we draw a sorption-desorption curve, if you still remember. Okay, we'll do it very briefly. So we had x-axis water activity, y-axis is equilibrium moisture content. And then we get these curves, which is sorption and desorption like that. Okay? And then we mentioned that we could cut down the water activity into 3 sections. And the first section we call it, this is a mono layer, an additional layer, and the last one is capillary, or we say free water area. Now what happened for the lipids oxidation, or we say which area is very sensitive to the lipids oxidation, which means the food products. The curve looks like this. That means for the food products which is low moisture, low water activity, between 0 to 0.25 is very sensitive to the lipids oxidation. Which means, talking about the food quality, we need to be careful, make sure they are not oxidized of their lipids. Right in the middle, the 0.25 and 0.75, this is we talk about is Maillard reaction. Now, at the end, if the products, their major water components is free water, or free available water, or we say capillary water, then it will be sensitive almost to every biochemistry reaction, including lipids oxidation, and also the passages. Okay, that's what we talk about the fresh produce and the meat. So this is very, very briefly. So we're going to focus on this curve today. Now we're going to talk about the definition. What is called lipids oxidation? Lipids oxidation is fatty acids in food products, in foods, spontaneously reacted with oxygen and will generate a series of the byproducts, including aldehyde. So if we want to draw the structure, you should know it is RCOH. Alcohol could be, which is RCHOH. Ketones, that is R, middle carbonyl group and R, and other chemicals. Of course, it will cause deterioration of food products. And we give them a terminology, we call it rancidity. Most of the time, lipids oxidation is not good, except one situation is frying oil. If you're using frying oil to preparing food, let's say you are cooking, you'll cause lots of lipids oxidation, but that is good for the food quality, tasting, whatever you call it. That's an exception, okay? Because this is you manually did it. It's not purposely you want to do. It's purposely you do it, not like accidentally happens. So this is the definition, and we're also going to give you some of the examples. What are the examples? Number one example: if you have a pig fat, which is lard. Someday you open the bottle, you taste it, you find it sweet. Does not mean it's like a sugar or candy, you can eat it. It's caused acidity. So lard becomes sweet. That is not good. Second, if you have a bottle of soybean oil, or let's say sunflower oil, one day you open it, you find it is fishy. Looks like a beamy, looks like a very viscously, and you also see it's like a sticky, and the whole thing turns turbidity. That's not good, which means the lipids oxidation has been happened. Okay, so that is the definition. Next one, we will be directly jumping to a general process, which means a general, or we say overall process of lipids oxidation. What will happen? Then we will talk about the factors for that. First step is always initiation. The initiation step is if you have fatty acids, we just say OH. The fatty acids, in the condition you have some oxidants, it will generate a free radical and release a proton. And this free radical, we call it alkyl radical. Now, by the way, what means a radical? The radical means you had an unpaired electron in their outer layer orbital. In outer layer orbital. If you have an unpaired electron in the outer layer orbital of the chemical, it's very easy to react it with other chemicals because they are in an energized, excited status. So that's what a radical means. Okay, now the second, we call it a propagation step. At this stage, you have this free radical generate. You're going to working with oxygen. And be careful, this oxygen has to be singlet, not triplet. We'll explain to you. So what are they going to generate? So you will generate ROO a dot. This is what we call perioxy radical. This perioxy radical is a little bit stronger oxidant itself compared to a free radical. Then this ROO free radical, they're going to work with another fatty acids chain. Usually it is in the same triglycerols. And what they will generate? They will generate ROOH and a new R. And this guy could be repeated to do the same thing. And what is ROOH means? Hydrogen peroxide. This is exactly the same thing of the PAA, the peroxyacetic acids we are doing in the lab for antimicrobials. But the principle we will talk about next couple weeks when we talk about antimicrobials. But it's the same thing. Okay, so this is propagation. This reaction could repeatedly happen. Now the last stage, of course, it is called termination. So what happened at the termination stage? It depends on what type of the radical you still have. If you have all dots, which means an alkyl free radical, they could work together, generate a dimer. This is a dimer. Now, what type of the situation this will happen? Usually, it is a low oxygen environment. Sometimes you can say if it's a vacuum package bag, however, you didn't vacuum seal it very well. You see the bubble sometimes generate from the side of the vacuum package. That will generate a dimer. Okay, the second end products could generate is we have all OO dots. They could react with another free radical, which means a peroxy radical working with another free radical. This will become ROOR. That is, we call it a alkene and peroxyl radical. This is usually happened is at atmosphere. Oxygen. Now last, if you have this guy comes out, ROO, in a certain condition, let's say in a frying oxygen, a frying oil. Frying oil, we had a lower level oxygen. However, we have extended a very heating time, which means a very high temperature. Then what happens? They will going through polymerization process. Polymerization then generate a polymer. That polymer looks like this. And this is a polymer. So, what type of the products will generate after you do the frying or you do the frying process? It will be very sticky. It's very gummy and viscous. So this is the overall picture, what it looks like: initiation, propagation, and termination. Then we're gonna move to talk about what type of the factors will impact the lipids oxidation. Number one, everybody knows oxygen level and oxygen type. Because based on the definition, it is a fatty acid spontaneously reacted with oxygen. Now, then there is a question always asked: how about we just remove all the oxygen? Is that means the lipids oxidation will not happen? No, does not mean that, because more or less oxygen will have, and sometimes we don't have an oxygen, but we have a different type of oxygen. We have a triplet, singlets, and even some oxygen ions there. That could be going through other biochemical reactions and generate oxygen type of chemicals. Still, they could cause lipids oxidation. But obviously, lower level oxygen will be decreased the speed and the rate of the lipids oxidation. But what we're going to talk about here is not oxygen level, is the type. And I just mentioned here, the easiest one to happen lipids oxidation is a singlet. So what this means? This is we need to go back to talk what we said in our exam 1, lecture 1. So basically, the oxygen, what we talk about, it is triplet, even in the atmosphere or in the chemical lab. And do you still remember what is the outer layer orbital? it is 1s2, 2s2, and 2p4. That's the reason why I have the question for you. Okay, what it looks like? We're going to draw a couple of things. What it looks like, if you still remember, up, down, the electron spin opposite direction. This is 2p. Okay, how they go? Up, that's Hund's rules, then they go down. Pauli exclusion policy. They are running spin opposite direction in the same sublayer orbital. Okay, this is called a triplet. Can triplet cause lipids oxidation? Yes, but the chance is very low. Because if triplicate is easy to happen, easy to cause lipids oxidation, they can directly react it with here. Why this thing not happen directly here? Because in here the model they are using is a triplet oxygen. There's not singlet. Okay, that's the reason you have to go here and here. Because they think the energy of the perioxy radical is higher than the triplet oxygen. Now what happened in the food products? In the food products, you more or less have some chemical called photosensitizer. Or you can say it is a photosensor. That means some of the chemical there, it's very sensitive to light. What are they? Usually it's a colorants. Myoglobin, chlorophyll, A or B. This is basically vegetables all have. This is basically meat products all have more or less. Then what will happen? It will be changed. How they change? 1s and 2s are the same. This is exactly the same, nothing changed. We don't have to worry about here, 1s, 2s. What happened here is this 2p. What are they going to do? And even the first sublayer is not changed. They are happening in the last two sublayers. They could become, even in a different sublayer, they run in opposite direction. So, you can simply see here, and here, there is a difference. This is, we write 1. Okay? But this is not major happen in the food products. In the food products, majorly happens is you go here, these two are the same, no difference, exactly the same. What happened? They will move together. Left empty sublayer orbital. This is, we say, delta 1. This is an existing. Why did it existing if the photosensor happens? And this has become a singlet oxygen. And the singlet oxygen is very easy to have lipids oxidation. If the triplicate, we say the rate is 1, and the singlet oxygen is 1,500. The reason is the singlet oxygen, they have the opposite direction of their sublayer orbital, or they have an empty layer without electron. Their status, we call it a highly electrophilic. And this electrophilic is matching the double bonds of fatty acids. They can react it together. They could be reacted, not only reacted, they could generate the configuration from cis to trans. This will give you an example later on. Okay, so the level of the oxygen is important, but the type of the oxygen is more important. This is the reason some of the food products you have to, using a container, avoid the light. Let's say the dairy products, most of the dairy products, you never see that in a transparent container. Because those dairy products made from the milk, they actually, the light will be sensitized. The oxygen there will, from the triplates, become singulates. Okay, so this is the first thing we want to talk about. Second factor, that's also obvious, is unsaturation. Now, obviously, we care about the ratio of unsaturated fatty acids versus saturated fatty acids. If in triglycerides, you have lots of the saturated fatty acids compared to you have a lot of double bonds. Obviously, you have a lot of double bonds, easily to have a lipids oxidation. This is from the energy standpoint, it's already been verified that. So for example, I have CH2, and CH2. The energy required to generate free radical is very high. That means almost 95 to 100 kJ per mole. If it's a saturated fatty acids, but does not mean it will not happen. So palmitic acids, stearic acids still could happen, but you need lots of energy. If I have a double bond there, let's say like this, the energy will be lower. The energy required to generate free radical will be only 85 kJ per mole. So that's the first thing. Second, the double bond's position also is a major factor. That means the location. And this impacted by the surrounding carbon. If you have CH2, CH double bond CH. Now, by the way, this is an example in oleic acids. This is a very sensitive carbon. It will become a free radical. Because this is, we call it an olefinic carbon. And the energy required to generate a free radical is even lower, is only 80 kJ per mole. Okay, so let's give you another example. We talk about the position and the location. If I have CH2, CH, double bond CH, CH2, double bond CH, CH, go here. This is more easy to happen. Why? If you know food chemistry, this is a very, if you know chemistry, organic chemistry, this is a very special name for that, called pentadiene. This pentadiene structure could be very easy to recognize by a very special enzyme. The enzyme called lipoxygenase. This is widely existing in peas, in beans, and also in soybean. Most likely in soybean, widely existing. This enzyme will cause lipids oxidation because they recognize a special structure called pentadiene. At this moment, they only need 70 kJ per mole, even less than that, will happen lipids oxidation, much lower energy. Okay, so that's a unsaturation ratio compared to the saturated fatty acids, the position and the location of the double bonds. This is the number 2. Now, number 3 is easy. What are you packaging? Okay, did you do vacuum package? Did you do aerobic storage? Or did you do modified atmosphere packaging? Obviously, vacuum package will have a much lower oxygen compared to modified atmosphere. But you know, usually the correct way to write a paper, a manuscript, and even you do vacuum package, you need to write the oxygen amount there. That was usually lower than 0.5%. Sometimes lower than 0.1%, but more or less you have some. Okay, this is usually in the lab we do the PVC film packaging, which is aerobic. Modified atmosphere packaging, we need those different pump to do it, to make sure the nitrogen, carbon dioxide, oxygen in a different combination. So that's a packaging. Number 4, it's also not difficult to understand, is storage. How you storage it, and storage, more important, is temperature. Now, basically, we will say the lower temperature is not easy to happen. Lipids oxidation, higher temperature, it happens. That's the obvious reason we know about that. Number 5, whether you have a pro-oxidant, which means in the food products, whether you have something already being ready to do lipids oxidation, sometimes you cannot avoid that. Or you put the products is already being halfway going through the propagation process. So you have a pro-oxidant there. Another thing, antioxidants. So whether your products already have antioxidants, if you have it, of course, lipids oxidation will be inhibited or slowed down, but it will happen anyway. So we give you an example. What happened is, if I have a free radical, and then I had like antioxidants like this, what will happen? This will be released, and this will become OH. So basically, this free radical goes back. Okay, but be careful. This is a reverse. So what this means, you cannot add too many antioxidants. If you add too many antioxidants, what that means, so reaction will go opposite. Therefore, for antioxidants, United States Department of Agriculture, Food Safety Inspection Service, USDA, FSIS, have a list which is approved to be used and approved dose, which means the concentration to be used, which is right above the antimicrobials, the same list. So you have a table which is for antimicrobials, which is, I always look, lactic acid, citric acid, or different combination. Above it is antioxidants. So a very easy example is the tocophenol. This is usually, they're using 10 to 50 parts per million. You cannot do more than that. If you do more than that, it will goes back. Okay, so just give you one very simple example to talk about the antioxidants. We'll have a slides to talk about that. Another thing I also want to mention, which is related to this number 2, the unsaturation. We had another research has been done, the energy required to generate free radical. Like I said before, you should be very clearly to know stearic acids is C18(0). Okay, let's say the energy required, we're using EE. Oleic acids is C18(1). And linoleic acids is C18 delta 2. And we have a linolenic acids, that is C18 delta 3 actually. Okay, we don't use delta, we just say 3. So we can remove this guy off, not confuse you. What's the energy required? Which means what's the rate of the ratio? Let's say stearic acid is 1. Oleic acid is 1 double bonds will be 100 times easier to happen, and the rate will be 100 times more than stearic acids. If I have a 2 double bonds there and the pentadiene status, this will be significantly increased to 1,200, the rate. How about I have 3 double bonds? 2,500. Dramatically increased. This has been done by the research in 1950s, 1960s. They talk about that. Okay? So this is what we all have these opening remarks to talk about that. Then, Ian, do you mind move? We're going to give you an example. Using the whole picture there to give you an example, to explain to you what really happens from the chemical standpoint. It will be a long drawing, but we have to do this. Okay. Usually, most of the textbook using an example is this is an example of lipids oxidation. By the way, I forgot to mention lipids oxidation. We also call it auto oxidation. Okay, that's another name for that. We were using sunflower oil as an example. This is, you can buy $5 is 1 gallon bottle from supermarkets using for cooking. Okay, obviously oil is a triglycerols. So what's the structure? C, C, C right there. Then you have H, 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 H. The middle one is chiral. Then you have O, and you go here is carbonyl group, or we say carboxy group. They originally is glycerol with fatty acids, lose water. Okay, now what happened is these side chain. This position you know, SN1, stereo specific number 1. What is that? Most of the time is CH16 go CH3. So what is that? Stearic acids. That's C18, 0. Okay, then the second SN2, what will happen is CH2, 6. Then you go here, CH2, it's carbon number 8. Then you go CH, double bonds, CH, number 9, number 10. Then you go here, CH2. Then you go here, CH2. How many you should have? 5. Because this is 11. So last one is CH3. What's the middle one? Oleic acids. C18, carbon 1. 1 double bonds. So that's easy to explain. How about the last one, SN3? What's the location? CH2, 6. Then go CH2. That's 8th position. Then go CH. CH. This is 9. This is 10. So we go here CH2, 11. So you go CH, double bond, CH, 12, 13. Then you go here, CH2, we need Basically, we need 4, and the last one CH3, linoleic acid, C18, 2. So you should know, sunflower oil looks like that, a triglycerides. Now, we're not going to talk everything together. In the real life, it happens all together. We will be only doing a model. So we're going to pick right here to talk about that, the procedure. So we pick this one, move down, goes here. Okay, so we skip several, but I need some space. So first stage, we skip some. We're going to have CH2, CH, CH, CH2. This is a long chain. We only take here. Okay, 8, 9, 10, 11. What's the first thing happen? Let's say the sunflower oil has been, you did not close the cap very well. You loosened. You put it in 35 degrees Celsius in the very summertime for about 3 months. Then you open it. You feel it's fishy, creamy. Even you can feeling about some phytyl compounds about it. What happened? They will generate, the first thing is a free radical. This is we call alkyl radical. This is the first thing, okay? Second, we have oxygen inside, it is there. We have lots of oxygen, but you did not close the cap. So what happened here? This will have O dots will generate. This is we call perioxy radical. Okay, this perioxy radical is very energetic. It could be using as an oxidant to react with another side chain of the triglycerides. Now, compared to SN1, SN1 is stearic acids, SN3 is easy to happen because it's a linoleic acid, have a pentadiene structure, have a 2. So what they do? They go here to this guy, okay? They here become a free radical. Now, they have something related to the chain migration. The cis will become trans. This we'll talk about later on. We skip talk about here. So what happened? Since you extracted, you have been extracted a free radical from there. So what's generated? OOH. This H from the top. This is hydrogen peroxide. Okay, once this hydrogen peroxide generates, what will happen? They will going through the first step is a deposition process. Decomposition. What they will do? They will cut here, generate OH. This is a free hydroxy radical. Hydroxy radical is very energetic. This guy basically can oxidizing all other chemicals. Basically. Okay, we will talk about antimicrobial principles behind this when we go talk about that. But I just gave you a hint here. This guy comes out. Okay, now what it becomes at this stage? At this stage, it becomes CH, double bonds, CH2, and don't forget, you have O here. What is this called? This is called alkoxy radical. Okay, at this stage, we're gonna move here. Okay, you're gonna draw. We have to draw the whole thing. So I'll maybe just draw right here the five position. We're gonna have to draw the whole thing. Okay, I draw a little bit long. I'm gonna have to move down here. So what we do? CH2OO. Just a little bit easy. Okay. This is we just write C and a bunch of stuff here. Okay, go here, the next one. CH2OO. C, I just write all three. Okay, this is linolenic acids, and we have to draw on the top. CH2OO, CO1. This is stearic acids. Okay, we're gonna draw here. We finished, and I'm gonna have to remove here because it's more clear. So let's draw it on top. CH2OO, CO1 goes here. CH2. Oh, sorry, CH. Oh, this is not CH2. CH. C. Just skip some. Okay, so it becomes CH. CH double bonds, CH and CH2 becomes CH3. Okay, now here we need to put this back. Okay, then we go CH2OO3. Okay, what will happen by the time? This is already at stage number 5. We're going through deposition. Okay, this double bonds right here. They could cut 2 different directions. They could slice right here. If they slice right here, a biological slice, okay, they will generate this product. What is that? Glyceride aldehyde. This is a non-volatile compounds. So you're not going to see this reacted in the final food quality. But what else will happen? It could cut from here. If they cut from here, they will generate the products. Is this guy. First of all, this cut, we call it hemolytic scission. Same as hemolytic, we talk about in the microbiology class. This is called beta scission. Beta slice, you can easily understand. What's the products you will generate? We can move down. CH, O goes here, then you go CH, double bond, CH, CH2. We could do a little bit more. Okay, CH2, CH3. That should be 6. What is this one? Aldehyde. And this aldehyde later on even could be further decomposition, become HCOOH. That is the easiest fatty acids, the simplest fatty acids we talk about formic acids. So, when we test the progress of the lipids oxidation, if you have a formic acid generate, which means you're already being at a later stage, and aldehyde contributes to the flavor change. That's not good when you have aldehyde generate. Okay, now we're going to talk about this guy. Usually what will happen? Number one, they could stay the same. This is what we call 2-uno-decano. From the chemistry standpoint, based on we learned International Unit of Pure and Applied Chemistry, we talk about the systematic number. This is called 2-uno-decano. Uno is number 1, decano is 10, so you add up together is 11 carbon there. That's the first thing will happen. Second thing what will happen? The migration, which means shift of double bonds. The shift of double bonds will cause what? A solid double bonds here, and here will become saturated. Yeah, that could happen. This is based on, in the environment, there's some free available oxygen, free available hydrogen, proton is available there. That could happen, the migration. Okay? Now, we want to talk about something else. This whole thing, we already talked about these separate. This whole thing is a big oxidant. And we already said, this is alkoxy oxidant. It's very energetic. Could to do lipids oxidation for other things. So how do you do it? We'll just give you some example. In order to explain this, we write, keep the middle right here. This right section, or 1. This left section, total, or 2.